So my name is Donțu Mihai. I lead the Linux development team at Bitdefender. We are doing security software utilizing open source technology. Today I'm going to present hypervisor-based security, vicarious learning via introspektioneering, or how I learned to love the... These are difficult times. You can't just use tactical nuclear device anywhere. Anyways, this is as funny as it gets. I'm going to go do a quick recap of how we got to do VMI on Zen, the current status of the VMI API, Bitdefender's approach to creating a commercial product using this API, and what we're really busy with right now. So the spark appeared around 2003 with a research that presented VMI as a method of doing intrusion detection. Around 2008, a university presented a POC using Zen 3.1, I believe, and also pushed some patches, mem event were called. In 2012, a number of companies, among which Bitdefender, started pushing even more changes into Zen and trying to build a commercial product. And in 2016, Bitdefender published the first security software using VMI with Zen in technology preview, using specifically Citrix Zen Server 7.0, Zen 4.6, I believe. So the current status of the API is fairly complete. For what we need, everything is in place. At least for x86, we have some people working on ARM, but I don't really know the status there. The basic API allows to trap and receive notifications when an MSR, a programmed MSR, gets modified, a control register gets modified. It allows the ability for code inside an introspected VM to call it to the introspection application. It allows to receive breakpoint events, EPT violation events, and it also gives the ability to veto. So for example, if an application, if an introspecting guest tries to change an MSR, the application doing the introspection using VMI can prevent that modification. And basic stuff like retrieving the register file, register set for vCPUs and TSC, so on. The approach Bitdefender uses is with a security virtual appliance, SVA, that is on an equipment, a single VM is dedicated to doing introspection, to analyzing all the other VMs. The introspection engine is actually a user space application. It connects to the event channel bus for receiving VM events, and it does its thing. The current effort at Bitdefender is focusing on VDI. Most of our clients, actually a good number of our clients, are using Citrix technology for VDIs, and we're looking into bettering our performance to better suit their purposes. So we find a couple of issues that we are actively working on. This is my personal testing rig. It's a Haswell machine with 32 threads, bunch of RAM, bunch of disk. And we're using Zen Server Dundee and standard VDI benchmarking software. I didn't put it in the presentation, but it's login VSI for those of you who know. We're all friends here, right? All right, the first problem we've hit was with the x86 emulator. So when we started doing introspection, we changed the permission in the hypervisor for a number of pages, and we started seeing that a number of applications, such as browsers, and even the Windows 10 kernel started doing that, doing writes using SSE instructions. And for legitimate writes, we would want to execute said instruction, but without changing the page permissions. So obviously, you can do that with the emulator, but in the case where SSE support is not complete, we had to do a number of workarounds. So yeah, the x86 emulator is pretty complex piece of code. As I told a number of times, it's really intimidating. It was forked around 2006 by the guys doing KVM, KuramNet, I believe. It was largely rewritten. So yeah. There's a work in progress for adding more support for missing SSEs instructions. And as a consequence, I think a number of issues that nobody connected at the time, for example, a crash with QXL, who's trying to do copies into the video memory. And I believe in Zen, the video memory is marked read-only. I'm not sure. But it traps whenever it...
It's trapped for log30 purposes, so QEMU knows a write into the frame buffers happens so it can update the VNC.
Okay. All right. So, but as I said, we are using Zen 4.6, so we're looking at a number of alternatives. The first one is complete hack. Pause all vCPUs, remove the page protection, single step, put the protection back and resume, unpause and resume. The second one is the one we hope to be using in the future. It's alternate EPT views. You're allowed to have different permissions, to change the permissions for the EPT for a single vCPU. So you can do a switch, single step, switch back, and resume. And it affects only one execution thread. We played around with it for Zen 4.6. Unfortunately, we hit a couple of snags and didn't really have time to research what exactly is going on. It's pretty deep hooked into Zen as well. So, all right. So a number of I put here some performance numbers. All right. So, for example, in EPT, a page is marked as read-only, and an application doesn't know that, it's trying to write in it. It traps into the introspection application. The introspection application checks the code, does the disassembly, say, okay, that's a legitimate write. Yes. Yeah.
Again, I think there are 2 APX instructions currently handled, and it's the same problem.
I hope we get away with only the move instructions. So this benchmarking software, what it does, it starts a number of VMs, runs in each one of them a workload, collects a number of metrics, and tells you at the end a number of things, among which is how many VMs can you run on that host until the user experience degrades too much. Our target was for a 20% penalty, and in the test we provisioned the VMs, 2 vCPUs, 3 gigabytes of RAM. So for the initial test, the baseline, so-called, the benchmarking software said, okay, this equipment can take easily 96 VMs, no problem. The second benchmark was with VMI enabled, our beloved work, and it said only 9 VMs can be run in this mode. Obviously, there was a little bit of panic and running around in circles. So we started hammering the introspection application, and we found a number of things that we were doing bad. One of them was we were doing a lot of hypercalls. So for each VM event that comes from a guest, we did several hundred hypercalls just retrieving the register state for a vCPU, the current vCPU. So we started caching those, and with a little bit of adjustment, we got to 50%, almost 50% performance penalty. Then we started filtering even more the MSR events. The initial API was all or nothing. That is, you either receive notification for all MSR changes or for none. So that didn't really work for us. We refined the API, so we don't receive notifications for MSRs that we're interested in. So R star, L star, syscenter, so on. That got us another 5 VMs, got us 55 out of 96. And the cherry on the cake was actually HVM get context partial, that even though it was retrieving data for a vCPU that was paused, and you should have been able to do that without any locking or IPI, it was pausing the entire domain before getting the data. That wasn't cool. So we did a little adjustment there, asked Andy's opinion. It was broken the first time. The third, fourth time was pretty good. So that got us to 90 and well within the 20% performance penalty. By the way, this test was done with protection only on the kernel. The kernel doesn't really change. It's pretty static. Once it's hooked, it's pretty easy to track. The next test was enabling the user space introspection. The user space introspection generates event for every process started. It also, by default, protects a number of core services for the operating system. In the case of Windows, there are, I think, 10 or so services. But as a custom application, we only use WinWord. And did the first test. The performance dropped drastically again to like 30 VMs out of 96. The first thing we did was we dropped get vCPU context. The thing is, every time a VM event is generated, to the structure that represents the event, a part of the register set is placed there, so you can use that without going back into Zen to retrieving the registers. That jumped us from 30 to 50. Another thing we did was also drop set vCPU context. Once you set the registers in the VM event and you reply to that event, Zen would copy the data into the vCPU state. There was a little bug there. There's a patch for Zen for the current Zen version that fixes that. So that got us to 86. And one of the surprising improvements came with switching the kernel. So for 3.8, we used the patch that allowed us to map pages below the first megabyte. Apparently, there was a limitation in the Linux kernel that didn't allow that. Switched from 3.8 to 4.4, where the Zen support has been largely improved. And that got us another 4 VMs, and well within 20%. And what we're fighting with now is support for many, many more processes, browsers, readers, all used at the same time like crazy. The first test, again, drop test. One of the things we did is we took a look at HVM get context partial again. So the thing is, whenever this hypercall is invoked from that domain, it checks if the current vCPU matches the one for which we are trying to do the read. The problem is that VM read doesn't have the notion of retrieve the data from that VMCS block. So it has to switch the VMCS, read the data, and then switch back. And when doing intense introspection, the time slice for the security virtual appliance to do its work gets smaller and smaller. So what we did, when the initial VM event is generated, we get the entire vCPU state, put into the VM event only the needed registers, and the rest we stuck into the Arch vCPU. So when we do HVM get context partial and we know the vCPU is paused and it's the specific vCPU, we check if the data is cached and just get that. Skip a VMCS switch. Another thing we did is that before we adjusted the permissions in EPT, we would get the information from Zen, but we rely on the fact that once they were set, Zen doesn't change them behind our back, so we can cache them in the SVA and simply rely on what we have there. And that jumped us a little bit more. And the last one, which some of my colleagues are working on, and I don't really have the numbers yet, is a version of setmem access that works in batch mode, so Sparks. So right now, say an application starts, the introspection engine says, okay, let me protect the old pages that make up the code area. So it'll be like 100 pages, 1,000, and for each and one of them, you'll do a hypercall, change the permission for this one, and each such hypercall generates, well, it takes a lock, it generates an IPI, all kinds of, it does a lot of stuff just to change the protection. So what we did, we created a version that receives an array of pages, the permission, does them in bulk, and sends at the end an IPA. Don't yet have the numbers for these ones. this optimization, but I'm hoping it'll be pretty good. So a little bit of a conclusion. A lot of the API we're using for introspection was not designed to be abused the way we do right now, especially the API that was specifically employed for migration. I think that was the purpose of HVM get context partial. There were a number of things that are not needed for a post vCPU, like that domain pause. There's a little thing that I've noticed. So in full load, the SVA, if I do a perf top, I can see that Zen hypercall Zen version is the most frequent hypercall. So I would have expected the event channel hypercalls, mask, notify, and so on, unmask, notify, and so on, to be the most used. But it's actually Zen version. I cannot tell if is that a problem or.
Specifically, events only get delivered on the return to guest path. So the kernel goes, sees an event is pending, makes a Zen version hypercall, which is the quickest hypercall to execute. So the event gets injected on the next return path.
Okay.
So it is very common and expected to see the Zen version hypercall at the top of the list. It's just unexpected if you don't know why.
Okay.
But yes, that is the kernel processing events.
So it doesn't, the initial interrupt doesn't trigger a special read.
It's more like injecting a signal into user space. Even injecting a signal into a POSIX user space, that happens on the return from kernel to user space part. It doesn't get injected in the middle.
Okay. Another thing we've noticed is that when doing introspection with many events and a lot of applications running in those VMs, the number of such events which correlate with IRQs is like 20 to 30,000 per second for one VM. So the first vCPU of the security virtual appliance jumps through the roof pretty fast. So I would have expected that simply by doing a little bit of tricks with proc, IRQ number, SMP affinity to do a little balancing. But that affected performance. So it's faster to have the first vCPU go crazy than just distribute the interrupts for some reason. And I ran to it. That's all. All right.
So you said you set read-only permission for EPT even for the mapping for the user.
Yes.
Was not really sure why you need to do that.
For stacks and heap, well, for stacks, no. Read only, read execute. For code, read only for data. That's just enforcement for basic PE mappings, so to speak. Okay, which has whatever has to be read-only, we make sure in EPT that it is read-only, which is read-only data. Or for code, read execute, and stacks heap read write, no execute. For example, Chrome does self-patching, so obviously if it patches code, we trap that and see it's legitimate and have to let it carry on.
How effective is the introspection actually preventing attacks?
Yes, it does. We have a lot of demos for, the technology is designed for APTs and 0 days. It's pretty hard to get 0 days before they happen to do a demo, so we only have demos with what we've discovered so far. But the idea is we prevent a lot of the use of a lot of patching techniques in order to achieve control of a VM.
Are they mostly for Windows or do you have cases for Linux?
Linux too, yes. All right, thank you very much.